Okay, so good morning, and today we will study Lie algebras and Lie groups. And this is actually a mathematical topic, but it is something which is intimately connected with physics. And the basic idea, the point is that when we study symmetries, etc., these actually underlie our study of symmetries in physics. And so I think it's useful to spend a couple of lectures understanding this, and I will use this to introduce the special theory of relativity in the later lectures. So I need this material, but this is also standalone. It's a very important thing. Plays important roles in quantum mechanics as well. Okay, so the idea is something very simple. It says Lie group is exponential of Lie algebra. So these two lectures will be trying to understand the ideas which lead to this, which will explain this formula. Okay, so this is not a mathematics course, so we start always with examples and try to see where that fits in. So we won't do the most general theory of Lie groups or anything. So we start with an example. Okay, so the example is SON. Okay, what is SON? It's a set of n by n real matrices such that real matrices are such that one R transpose R should be identity, and what is the other condition?
Determinability.
Yes, okay. Okay. So this is an example. An important remark is that ON is not a Lie group. Okay, so this is the example, and we will work this out and we will see how this goes. Okay. So we will start with now I'll write the formula. So okay, then R can be written as e power a, where a is a real antisymmetric n by n matrix. Okay. Have we discussed exponential of a matrix in this course? Okay. So let's do that. Yes or no?
No, sir.
Okay, good. We don't need to, even if you don't know, it's fine. So I have to tell you where e power of a, here a could be any matrix, not necessarily antisymmetric. This is definition. Okay, summation. So identity plus summation m equal to 0, sorry, 1 to infinity. Okay, so this is looking ugly, so clean it up. Okay, so you can see that, so you compare with right? So it's like generalizing the power series for an exponential, and but there is an issue of convergence. Okay, so I'll just mention this. The radius of convergence is infinity. So the claim is that this kind of thing is a convergent power series. Even though we are expanding matrices, term by term, if you add, as you keep adding more and more terms, it will get closer to the actual value. Okay, so this is the definition. Is this clear? So this is a claim that one is making. Okay, so this is an example of this formula here. Lie group here is so arbitrary element of the Lie group is R, and arbitrary element of the so-called Lie algebra is an antisymmetric matrix. Okay, so we haven't defined. Okay, so the idea here is that some notation. Okay, so uppercase letters for Lie group. And lowercase letters. Okay, so I will write something now. So S-O, capital S, capital O-N is exponential of little s, little o of n. Okay, where SON equal to set of n by n antisymmetric matrices. Okay, is this clear? Okay. So is the claim clear? I mean, I'm just writing out things and putting more structure into the definitions.
So is it necessary to use same notation for antisymmetric matrices?
Yeah, because I mean the idea is that there is this nice connection between so the Lie algebra of SON is related to the Lie group of SON. So the same, you use the same letters. Okay, so we will see other examples. For instance, symplectic, we'll use capital SP, lowercase p, but then for the other case we'll use small s. Symplectic. We'll see unitary again, capital U and lowercase u. We'll see a few more examples. Okay, so let's work out some properties. Of e power a. A is any matrix, not necessarily antisymmetric. Okay, so I just want to write some properties. Okay, so the first easy property is e power a. If you want to transpose it, okay, that's equal to e power a transpose. Proving this is very, very simple. You just go back to the definition. You transpose this side, and term by term you transpose a power m. So proof is easy because a power m transpose is equal to a transpose power m. Okay, so this property is very easy. Okay, so let A be any n by n matrix. Okay, so we want to multiply. So the thing is, what is e power a times e power b? Okay, so the naive guess. Does anybody have a guess? Naive guess? Anybody?
E power a plus b.
Exactly. Okay. And this is not true. but true if A and B commute. That means commutator of AB, which is AB, you know this, right? Equal to 0. Okay, if A and B commute is what we would say. Okay, so is this point clear? So what is the correct formula? Okay, it's complicated, but exists. Okay, and it's called the Baker Okay, so life is not so bad. E power A times E power B, at least the following holds. It can be exponentiated again, where, okay, the first term there is A plus B, the next term is half anticommutator of A and B, okay, next plus 1 by 12 commutator of commutators, A commutator AB, okay, plus minus B commutator AB. Plus the formula doesn't end here, plus an infinite series of terms. Okay, is this formula clear? So the first point is that, at least the good news is that e power A, e power B can be re-exponentiated. Okay, that is the first point. And so the point here is that if you look at the pattern here, so you see that the first non-trivial term, A plus B is the term here, is the commutator of A and B. But if you look at the next term, it also has the commutator of A and B. Okay, so what you can see here is that if AB commute, that means this term vanishes. Actually, even the substituted guys, because A with 0 is 0, B with 0 is 0. In fact, all the other terms that I have not written also will contain commutator AB. Okay, so that is the, okay, so you can see this formula, but there's another example. Suppose AB equal to constants times identity. Okay, suppose A and B are two matrices, they don't commute. Okay, C is 0, it will become that. So now we look at the, okay, so the BCH formula says, put a tilde here, okay. Okay, C equal to A plus B plus half B tilde. That's it. No more terms. Okay, have you seen anywhere something like this? The commutator of two matrices giving identity being proportional to identity. Have you seen this? In some other course? Exactly, okay. Yeah, so let's write that. So, okay, except those are infinite dimensional things. So carry forward is xp equal to IH bar times identity in Qn. Okay, is this clear? So the point here is you should, something which I would like you to do is to actually derive this formula up to the order that I have said, okay, which is three terms, right? One, A plus B is the 0th order term, so this is order first order and this is second order. And what do I mean by the orders? So let me explain this to you. You just put lambda here, and put lambda here. Okay. Then what you will observe is that these terms are lambda power 1. These terms are the coefficient. At the end of the day, you can put lambda to be, this is lambda square, and this is lambda cubed. Okay, so the way to do this is go back to first principles, write the definition of e power a, e power b with the lambda, of course, and then check that when you expand it and try to re-exponentiate order by order, and then you will get these formulas. Okay, this is clear. The method of doing this is to introduce a bookkeeping parameter lambda in this case, and then you just track terms of order lambda or collect terms of order lambda square, so on and so forth, re-exponentiate and put the correction terms. Lo and behold, you will see all these terms emerge. Okay. So one reason e power a, e power b cannot be easy way to understand this is because e power a, e power b is not equal to e power b equal to e power a. Right? These are e power a is a matrix. Matrix multiplication, they don't commute with each other, right? If your order matters, right? Right? You agree, right? That order matters.
Yes.
Okay. So this is the second property you can do. Third property is really a cute one. Okay. It says that determinant of e power a, again a now, here is an arbitrary, this is equal to e power, okay, trace of a. Okay, so this is kind of cute. Okay, so example of this is to say that if a is antisymmetric, then what can we say about trace a?
Zero.
Okay, so this implies determinant of e power a equal to plus 1. Okay, so you can see that exponential of an antisymmetric matrix, and by an antisymmetric matrix will always have determinant plus 1. That was one property which we had for an special orthogonal matrix. Now you can see why ON we can never achieve determinant equal to minus 1. Right? So ON will not work, SON will work. Is this point clear? Okay. Yeah. Any question, comment? Okay. So we just will do a small digression to complete the proof. Okay. We will show that e power a is an SON matrix. Okay, so we need to check. We already checked this thing. So e power a transpose. Okay, what is this equal to? E power a transpose, which is equal to a transpose is antisymmetric. A is antisymmetric, so it's equal to e power minus a. Okay, so we want to show that this is the inverse of e power a. So this is equal to e power minus a dot e power a using this calculation here. Okay. What is this equal to? We can use DCH formula, right? It's e power 0. And e power 0 is identity matrix, right? Okay. So this concludes. So we have proved determinant is plus 1 versus 1. We have not proved the, okay. So every SON matrix appears this way. Okay. So this is a claim. So what we have shown is e power a. If A is antisymmetric n by n real matrix, then the e power a is special orthogonal. But we have not proven that all special orthogonal matrices are of this form. So I'm claiming this without proof. Okay. This is if it's a math course, I think we would have proved it. But here it's just for we are a physicist, so for us this fact is important. Okay. So is this point clear? Okay. So let me now give a hint for the proof. That determinant that of e power a equal to e power trace of a. Okay. So when I say hint, it's not going to be a complete proof. Okay. So suppose A is diagonalizable, okay, what does that mean? Okay, that means it's a normal matrix. Okay. Have you seen what a normal matrix is? Do we know what a normal matrix is? A commutes with A transpose. Okay. If it's complex matrices, it's A star transpose. Okay, diagonal or whatever. Okay, suppose A is diagonalizable, that means then A can be written as some orthogonal, special orthogonal matrix times some diagonal matrix times O. Okay, these are the eigenvalues, right? So these are eigenvalues of A. Okay, so now let us do the following thing. So let us, so we are given that e power A, and we are told E is OD. We know, you know this theorem, right? This we discussed several times in this course, right? We can do. So this is nothing but the matrix of eigenvectors. Okay, and there will be as many eigenvectors as eigenvalues. So we can always create O as an, so e power A can be written as e power O transpose dot D dot O. Now you go back to the original definition as exponential, and so this you can show is equal to O transpose dot e power D dot O. Why? O transpose is identity. That's all we need. Okay, so when you, so suppose you took, let's do, for example, a term which is A square will be O transpose dot D dot O dot O transpose dot D dot O. So what happens? What is this? Identity. right? So this is equal to O transpose D square O. More generally, okay, so that says the same. So this is what we get. So now det of e power a equal to that of O e power d times O transpose. Oh, right. Is this okay? I'm using this formula, rather this second version. Okay. But now the determinant of ABC we can cyclically permute. This is equal to determinant of e power d dot O transpose dot O. Okay, but what is O transpose O? Identity, right? Okay. Exercise. Show that e power d is nothing but, it's also a diagonal matrix. Exponentiation of diagonal matrix is very easy. What I have not written are zeros. Okay, so what is determinant of e power d then? Somebody?
E raised to d1 plus d2 dn.
But what is, how are d1, d2, dn related to the matrix A?
Trace.
They are the eigenvalues, right? They are the eigenvalues. d1 to dn are the eigenvalues. And so this is nothing but sum of all the eigenvalues is e power raised. This again we know. Okay. So more generally, any matrix A can be brought to something called the Jordan canonical form. Or Jordan, that's the correct spelling pronunciation, but in English we say Jordan. Okay, and so that would be, this is usually in some convention, it's upper triangular matrix with eigenvalues in the diagonal. Okay, so when you take determinant of that guy, again it will come back to this thing. So same formula holds.
Sir, here O matrix belongs to capital SON or small SON?
Capital S1. This is the group element. Okay.
But sir, O is A is related to O, and we are
A is
writing.
not related to O. I mean, in the sense that O is the, so here's how I defined it. Yeah. Any matrix can be written as some orthogonal matrix. There's a particular decomposition for a normal matrix. A, O, D, O transpose. That's what I claim. This you know actually. You can go back and check this. Have I answered your question?
Sir, A belongs to small SON, right?
A doesn't, A at this point is just some no SON, nothing. A is some arbitrary normal matrix that can be diagnosed. That's all. N by N.
Okay,
Real
sir.
matrix. There's nothing to this. Okay?
Okay, sir.
Yeah, but when we specialize to the case of SON group, then A will be little SON as you corrected it. But this is this property. These are properties which I'm just for any matrix this is true. So this formula that we have written, property 3, okay, this is true for all matrices. Okay, is the point clear?
Yes, sir.
Okay, good. Okay, so okay, so back to the discussion. So I wrote out some properties of the exponential. Okay, so let us just quickly see how. Let's do some examples again. So go back. Let's do SO2 first. Okay, so we have to write the most general. A is some real number. Okay, so we need to work out what this is A. Okay, but there's something nice that happens. Let's look at A square. Okay, so you will see that A square is equal to minus little a square times identity. Okay, it squares to minus 1. This property is very, this kind of tricks that we will use is very easy. So it says that e power a, okay, so we'll write it now as follows. I'll break it up into I shouldn't do it this way. No, let's write it out. Okay. Sorry, I'm being really kind of. Okay, so let's look at some terms. What is a square? This is minus a square times identity. What is a power 4? A power 4 times identity. What is a cubed?
minus a square capital A.
A cubed. Okay, little a cubed. Capital. That's correct. Okay, so we can now go back and we can collect terms. So there are terms which are proportional to A and proportional to identity. So we'll collect terms like that. Okay, so first term identity 1.
So shouldn't it be minus a square a cube?
Hmm?
A cube shouldn't it be minus a square into a?
No. Ah, yes, yes. Okay, yeah, good. Next term is okay. And so I'll write one more term which I haven't written here. times. Okay, I pulled out the A for some reason. Okay, so now you can, if you look at the first term, what do you see? First three terms are there. We have written three terms. This is the expansion of something which you should know, which is
Cos A.
Cos A.
okay, and the second term is sin A. So A is just the angle of rotation. Okay, we know from other considerations that this is the most general SO2 matrix. We know it beforehand, but lo and behold, what we get is this thing. Okay, so is this clear? So let's do one more example. SO3. And so here, what is the most general antisymmetric matrix? A okay, so we have to put the non-zero entries will be here. If I give you these three numbers, below that you can get by looking at this thing. So I will use some convention and write those terms. Okay. So this guy is the 1, 2th element. This is the 2, 3 element, and this is the 1, 3. This is 1, 3, and this is 2, 3. Okay. So what we will do is we'll call this star element, we'll call it A3. Okay, it's like the cyclic permutation 1, 2, 3, 1. So 1, 2 will be called 3. What should we call A2, the 2, 3th guy? A1, okay. And this guy is now 1, 3, which is the opposite. 1, 3, 2 we would have written, but we can put a minus sign. This convention, okay. Is this clear? So this is some convention I'm following. You could have put, I mean, there's nothing wrong in putting it as plus A2, but there's a reason for doing that. So A, the most general guy, will be 0, A1 minus A2, and antisymmetry. So this will be plus A2, 0 here. This will be A3, this will be minus A3, 0, sorry, I messed up. Okay, so there are three free parameters. Okay. So this is a 3 by 3 and most general 3 by 3. Okay. So is there some trick that we can use which is analogous to what happened here? We saw that A square satisfied some equation. Okay. So A is a 3 by 3 matrix. Okay. So there is this nice theorem which says that it's called Cayley's theorem or something like that. I don't know. Any matrix satisfies its characteristic equation. What is the characteristic equation of a matrix?
Determinant.
Determinant.
Okay, so it will be some degree an equation. Okay, it will be the same degree. So what we will see is that in our example, A will satisfy What is the degree of the equation? The third order equation. Okay, what does that say? It says that a square, or a cubed, okay, will be in general a cubed what will it say? A cube should be expressible in terms of a square, okay. A cube should be expressible as identity a power 0, something with this thing, plus something with a, these are all arbitrary numbers we have to put, plus a square. Is this clear? This is what will happen. Does this make sense? What I'm saying?
Yes.
Okay. So e power a will be now something more complicated times identity plus something else times a plus something else times a square. So we can work out these arbitrary guys and see how we can work this out, and you can actually write closed. Okay, so we can write in fact. Okay, but we know that okay, because this is supposed to be a rotation matrix, and we saw that we know a formula for this, right? This is arbitrary rotation matrix, right? Okay, so now we need to, so let me just start now. So we have this A, we wrote the most general 3 by 3 antisymmetric matrix. So it has how many parameters? A1, A2, and A3. And you come back here, and lo and behold, we see that this also has how many parameters? Theta is 1, and a unit vector which is 2. So there are 3 such parameters. So what you can do to make this analogy work, you write something like this: A1, A2, A3 to be theta times okay. If you do this thing, then you should be able to match. Okay, so this is make this choice. Okay, so I'm giving you, this is the map, and what should theta be? Is this clear? Okay. So, because I want n1 square, n1 square plus n2 square plus n3 square should be 1. So that just takes care of this. Okay. So more general, so we can write A can be written as theta times n hat dot t. Okay, where T1 is an antisymmetric matrix with only zeros and ones. So first thing we'll write this way. T1 will have its first row and column to be 0, and this will be 1 and minus 1. T2 will have second row and second column to be this thing, and the rest of it should be antisymmetric, so diagonal should be this way. And T2 will be, this is 1, 3, so it will be minus 1, 1. Okay, and let T3, Third row and third column should be zeros. Diagonal should be 0, 1, minus 1. Okay, if I do this, you can easily check this. It's not so hard. Okay, is this clear? What I've done, I've just I've completed the map which relates A and the n and theta. Okay, but I had to introduce this 3 by 3 matrices, and this is the analog. Even in the 2 by 2, we had to introduce one particular matrix. I could have called this T if you wish. Okay, so but here we get a triplet of such matrices, and so this is so next lecture we will see the appearance of additional structures. That go into defining a Lie algebra. Okay. So in the naive physicist sense, there would be, we would have thought we have finished this thing. Maybe there will be little visiting, group multiplication is associative. So we can ask, does it mean something? So, but those are all, so this is where mathematics is important, where they do things formally. And so it's important that we understand what they are doing, at least understand their definitions. Okay, motivations, etc. It's much harder for us as physicists to understand. Okay, so but this I'll just stop here today with some properties of SON. Okay, what was SON? The set of n by n real antisymmetric matrices. Okay, so this is the first thing. But now the point here is that it is a real linear vector space. Why? Or how? Okay, A1 plus A2 belongs to SON. If so, A1, let A1, A2, A3, etc. belong to little SON, that means n by n antisymmetry. So you can see that the sum of these guys, and of course, if C is some constant, C A1 also belongs to SON, C belongs to real. Okay, so these are the two properties. There are extra two. Okay, we will study the other properties next lecture. Okay, so I'll stop here and pause for questions. Okay, we have seen what a linear vector space is, right? So linear vector space is just some addition element. So it's like a vectors, and we can add vectors. We know how to add them. We can add. Yes, Yasser. Go ahead, ask the question. Yasser, you should unmute. You raised a hand, so please unmute and ask a question. Or even if you haven't asked a question and came by mistake, you can tell me that. You can unmute and tell me no, there's no question. Anyone else has a question?
Yes, sir.
Yeah, go ahead, Divakar.
Sir, in the beginning you wrote something like Lie group equal to exponential of Lie algebra. So by that, did you mean that if like in this case we'll see that if any element of that Lie group can be written as exponential of an element which belongs to some Lie algebra, or is there like
That's it. That's all. That's all that means. Absolutely, you got the essence of what I wanted to say. Okay, and the thing is that the Lie group is not a vector space, but the Lie algebra is. So we can add vectors. We can do a lot of things we do with vectors, which you could not do. So some things are easier to do with the Lie algebra. Some properties. Okay. Yeah. Anything else?